In these sections, we're going to start taking a look at lifting problems, another application of our integrals. And of course, we're still not moving away from the force times distance for our work because it certainly requires some work to lift something up vertically. But another way that we could write this is that the work is going to be equal to the mass times the gravity. Okay, so M is our mass. Gravity is going to be the gravitational constant, 9.8 meters per second, 32 feet per second square. Okay, or Y, which is going to be the vertical distance. Okay, so mg is our force. All right, and then mass times gravity is force, and then our Y is going to be our distance for this. Okay, now that works if we have something that's static. Okay, so for instance, if we're like hauling like a bowling ball up, all right, and we're just hauling it up using like some sort of negligible sort of weight to be able to pull it up, then that might be an example of that, but that usually doesn't happen. So a lot of times what we have to do is we have to vary what the weight is, okay? Or in this case, it's going to be the force, whatever's pulling down on the gravitational force. So, but what we can do is we can kind of partition that, all right? And the work, remember, we have, if it's m times g, the mass times the gravity, we can just go ahead and use some sort of force function. Okay, so we have this rho, which is going to be our density, which kind of helps us to get our force, the gravity, which we already know, and then this is going to be L minus Y sub I. That's basically going to be the length or distance. Okay, so force times distance, and then delta Y would be like the partitions of those distance. So, of course, we want to partition this into an infinite number of segments, and that's going to give us this Riemann sum for the work. All right, so remember, this is going to be our density, and then we have our gravity, and then we have the distance, which is going to be partitioned equally. But as an integral, we could just go ahead and set it up like this. All right, so we have to know what's going to be the density function. All right, but we also have to know what the force due to gravity is. We have to know the length, etc. for this. Okay, so let me show you an example of how we're going to set this up, and it's not meant to be too difficult for you all. Right? So we have a chain that's going to weigh 1.5 kilograms per meter, and it's used to lift an elevator that weighs 275 kilograms, and compute the work done when the elevator moves up 30.5 meters. All right. Now, there's actually two things to consider when you're pulling this up, okay? The first of which is the chain, all right? The second of which is going to be the elevator, all right? But we'll hold off on that. And when we pull the chain up, all right? So let's just say that like these are the links to the chain, all right? As we pull it up, whatever this elevator shaft is, all right? So usually what's going to happen is the chain's going to go over here. And so what's going to happen is as it goes up the elevator, all right, some of the chain is going to be over this side, all right? And as it keeps going up the elevator, we're going to get less and less chain, okay? So that means that it's going to be like a variable sort of force, okay? Or a variable amount of work that's going to, a variable force that's going to be needed to pull this thing up, all right? So to be able to figure out what's going to be the work necessary to pull this chain up, all right? Now, clearly, I think it's pretty obvious that the distance is 30.5, all right? So this is going to be the integral from 0 to 30.5, all right? And then also, what we need to do is we need to say that there's going to be some sort of force. And in this case, the force is going to be the weight. So that's going to be 1.5 kilograms. We have the gravitational constant, 9.8 meters per second. And then finally, we know that L is going to be 30.5 minus y dy. Okay, so that's going to be our integral for this. Okay, so again, this is our density function. This is going to be our gravitational constant, and then this is going to be the length. Okay, now we can go ahead and we can just multiply 1.5 times 9.8. All right, and that's going to give us 9.8. That's going to give us 14.7. So we get 14.7 integrals from 0 to 30.5 of 30.5 minus y dy. And when we integrate that, that's going to be 14.7 quantity 30.5y minus 1/2 y squared from 0 to 30.5. Right? Good news is that this is polynomial, so 0 is going to cancel it out. 30.5 doesn't make it too difficult to compute either. So we get 14.7, 30.5 times 30.5 minus 1/2 30.5 squared. All right. Now, some good news is that if we want to try to do as much of this by hand as we can, this is just 30.5 squared. So we can just really rewrite that as 30.5 squared. And we really have 30.5 and minus half of 30.5 squared. So we really end up with 14.7 times 1/2 of 30.5 squared. All right. And that's a little bit easier for me to do in my ultra sophisticated calculator. All right. So I'm going to take 14.7, divide that by 2. I'm going to multiply it by 30.5. I'm going to multiply it by another 30.5. And we end up with 6,800. And I already lost it, 37.3375. All right. And notice that we're still in kilograms, we're still in meters. All right. So it's going to end up still being joules for this. Okay. All right. And remember, anytime that you keep your unit standard, so remember, kilogram is a standard unit, meter is a standard unit. All right. A Newton is a standard unit, then you're still going to end up in standard units for this. All right. So that's not too bad with respect to these lifting problems. So that's all you have to do with this, at least the chain. But we still have the elevator, right? We never finished it all. Okay. Now the elevator is static. All right. So this is the chain, right? But the elevator, right? So force or work, excuse me, is going to be equal to density times gravity times distance. All right. And the elevator is going to be static. Okay. So the weight of the elevator doesn't change. All right. No matter what. Since the length of the chain is changing, all right, as we go up, that's why it's dynamic. Right? Well, in this case, we know that the weight of the elevator is 275 kilograms. All right. We also know that the gravitational constant is 9.8. And then finally, the distance y is going to be 30.5. All right. And I'm just going to throw that in my calculator. So that's going to be 275 times 9.8 times 30.5. Right. And so the work needed to pull the elevator up the chute or the shaft or whatever it is going to be 82,197.5, which makes sense. It should be significantly higher than the chain, right? Because we got to figure that the chain, if it weighs 1.5 kilograms per meter and you're pulling it up 30.5 meters, it's probably going to be like 45 kilograms or something like that, probably more than that. This is significantly more than 45 kilograms. All right. So just in your head, that should make sense that pulling the elevator is going to take a lot more work than it is to pull up the chain. All right. So finally, we need the chain plus the elevator to get the entire amount. And so that's going to be where we take our 6.8. So we're just going to take this amount that we just got, the 8.1 or the 82,197.5, and we're going to add that to 6,837.3375 and 89,034. All right, so that'll be 89,034.8375 joules. All right, to be able to pull that up, whatever the elevator, the distance is. Okay, so sometimes whenever we have like these static forces, we have to go back and we have to use our old work formula. But if it's a dynamic thing where, in other words, we're losing something or the chain is just going up there, up the shaft, and we're just shortening the length of the chain, then we're going to use this formula.